Bismillahirrahmanirrahim. We have to discuss exact differential equation. The expression m dx plus n dy is called exact differential if there exists a function f such that df is equal to m dx plus n dy. The differential equation m dx plus n dy equal to 0 is called exact differential equation if m dx plus n dy is exact differential. The differential equation y cube dx plus 3xy square dy equal to 0 is exact differential equation because the expression y cube dx plus 3xy square dy is exact differential of the function xy cube. That is, differential of xy cube is equal to y cube dx plus 3xy square dy. Equation 1 becomes, this is equation 1, so it will become differential of xy cube is equal to 0. Equation 1, that is, this is equation 1, and division by y square becomes y dx plus 3x dy equal to 0, and this equation is not a exact differential equation. Here we have equation number 1. This equation is exact differential equation because the left hand side of this equation is differential of the function xy cube. So this is an exact differential equation. If we divide equation number 1 by y square, so its equivalent form is y dx plus 3x dy is equal to 0. Now this is equation 2, and it is not exact differential equation because we are unable to write the left hand side as a differential of certain function. So equation 1 exact, if we divide 1 by y square, we get a differential equation which is non-exact. Equation 1 and 2 are the two different forms. One is exact differential equation and other is not exact differential equation. Thus we need a test to check a differential equation is exact. For example, second example, 2xy dx plus xy square dy is equal to 0. This is equation 1. It is exact differential equation because we can write the left side of this equation by differential of x square y is equal to 2xy dx plus x square dy. This equation 1 is exact differential equation because we can write the left hand side as a differential of function x square y. Dividing 1 by x, if we divide this equation by x, we get 2y dx plus x dy equal to 0. This is an alternate form of equation number 1. This equation is obtained by dividing 1 by x. Equation number 1 is exact while the new equation is non-exact. So here we have two equivalent equations. The first one is exact differential equation because we are able to write it as a differential of some function, while the second form of the equation is non-exact because we are unable to write this the left side of this equation as a differential of certain function. Now we have a theorem. The necessary and sufficient condition for the ordinary differential equation this to be exact is del m over del y equal to del n over del x, where m and n possess continuous first order partial derivatives, where m, n, del m over del y, del n over del x are continuous function of x and y. In this theorem, we have the necessary and sufficient condition for the ordinary differential equation to be exact as this one. If we take equation 1 as exact, then we can write this equation. So the condition is necessary, and if we take this equation we can arrive to the result exact differential equation. So here the necessary and sufficient condition means if we take the differential equation as exact, then we can write this equation, and if we write this equation we can reach to exact differential equation. So here we have two conditions, the condition is necessary and condition is sufficient. Let's prove this theorem. Necessary condition. In the given theorem, necessary, we start from the necessary condition. Let equation number 1, this is equation number 1. Now we start from this equation to be exact, and we have to prove that del m over del y is equal to del n over del x. Now let's start from the necessary condition. Let equation 1 is the exact differential equation. By definition, there exists a function f such that df is equal to m dx plus n dy. Whenever we have an exact differential equation, then the left side of that exact differential equation is expressible as a differential of certain function. Since equation 1 is exact, so we can have a function f such that df is equal to m dx plus n dy. Let's name this equation as equation number 2. From calculus, total differential, that is df, is defined by df is equal to del f over del x dx plus del f over del y dy. This is equation number 3. Comparing equation 2 and 3, here m, value of m, here value of m is equal to, here value of m is equal to del f over del x. So this is the value. Now we have value of n. What is value of n? This is n whose value is this is the value of n, and thus n is equal to this one. This equation holds because equation number 1 is exact, and from calculus we can write this result. If we compare equation 2 and 3, we can write m is equal to del f over del x and n is equal to del f over del y. Now differentiating m with respect to y, so we can write del m over del y is equal to del square f over del y del x. Similarly, differentiate n with respect to x both sides, we can write del n over del x is equal to del square f over del x del y. We have to differentiate this equation with respect to y, and we have to differentiate this equation with respect to x. Since m and n possess continuous first order partial derivatives, that is del m over del y and del n over del x are continuous function, thus this equation holds, that is del square f over del y del x will always be equal to del square f over del x del y. Now replacing this equation by its equivalent value, this is equal to del m over del y and this is equal to del n over del x. So here we have taken the necessary condition, that is we have supposed that the equation is exact. Here we have taken the differential equation is exact, and we have reached to this result. So here we have discussed the necessary condition. If we consider the equation number 1 as exact, then we have proved that del m over del y is equal to del n over del x. Now we come to the sufficient condition. Here we have the sufficient condition. This is a condition is sufficient. By the sufficient condition, we mean we have to take del m over del y equal to del n over del x. We have to take this equation and we have to prove that the differential equation is exact. So let del m over del y is equal to del n over del x. Suppose that integral of m with respect to x is equal to v. Suppose that integral m is equal to v is partial integral of m with respect to x treating y as constant. Now differentiating this equation with respect to x, we can write del v over del x is equal to m. From this equation, if we differentiate this equation with respect to x, we can have del v over del x is equal to m. Now differentiating this equation with respect to with respect to y, we can have del square v over del y del x is equal to del m over del y. We have to differentiate this equation with respect to y, so this is the result. Now replace del m over del y by its value, that is del n over del x. So we have an equation del square v by del y del x equal to del n over del x, integrating both sides. So if we integrate this equation, integration of del n over del x is equal to n. Similarly, integration of left side is equal to del v over del y. If we have to integrate this with respect to x, we get del v over del y plus some constant of integration. Here constant of integration is function of y alone. Since here the integration is with respect to x, so we can take the constant of integration as a function of y alone. This pi of y is some function of y alone. So this is the sufficient condition, and we have suppose that integral of m is equal to v. If we differentiate with respect to x, we get this result. If we further differentiate this with respect to y, we get this result. If we replace this by its value, and if we integrate this with respect to x, we get this equation. Here pi of y is constant of integration. Now taking this equation, putting the value of m is equal to del v over del x. This is the value of v. This value of v is here. So for m we put its value, and value of n. Here we have value of n. So here we have value of n. Now simplifying, so we get del v over del x into dx plus del v over del y into dy plus pi of y into dy. Now we come to the next slide. This is the equation. Now dv, what is this? Here if we if we look to this bracket, del v over del x into dx plus del v over del y into dy, this is differential of v. This expression, this bracket gives differential of v, and this second term will be as it is. So this equation is equal to differential of v plus pi of y dy. Now writing d here with integral sign, we can write this term as differential of this one. Now taking d common, so this is the expression which have been expressed as a differential of some function. So this expression is an exact differential of this function. Hence this equation is exact differential equation. Here this is the expression which have been expressed as a differential of certain function. So this is exact differential of the function this, hence this equation is exact differential equation. So the method for the solution of exact differential equation, method for solving exact differential equation: step 1, integrate m with respect to x keeping y as constant. Step 2, integrate with respect to y only those terms of n which do not contain x. We have to take those terms of n which do not have x, and we have to integrate with respect to y. Step 3, result of step 1 plus result of step 2. We have to add these two results, and we have to equate it to some constant, or we can write m dx plus n dy as differential of the function this, which will be equal to 0. We can replace this expression by its value. Here we have this expression whose value is this one. So this is the equation. Now putting the replace left side by its value, on integration we can write v plus integral pi y dy is equal to c. This c is integral of 0. Integral of 0 is equal to c. Now we come to the next slide. Integral of m v. What is v? V means this is v whose value is integral m. So putting the value for v, we have to put its value. So this is v putting its value. So its value is m. Integral m dx plus integral of pi y dy is equal to c, and this v have been replaced by its value. So this formula, it gives the solution of the exact differential equation, where this stands for the integral of m with respect to x, keeping y as constant, and this stands for those terms of n free from x. In symbols, solution of the exact differential equation is equal to integral of m dx, where y will be taken as constant, plus integral of the terms of n not having x into dy is equal to c. Now we have to solve the few questions. Solve the initial value problem. This is a differential equation, and here we have the differential equation together with initial condition. So it is initial value problem, and we have to solve it. In that equation, here this is value of m. The first bracket is value of m, the second bracket is value of n. So this is m, and differentiating this equation with respect to y. So this is the value. Now value of n is equal to this one. Differentiate n with respect to x, so it is the value. We see that del m over del y is equal to del n over del x. Thus equation 1 is exact. What is equation 1? This is equation 1. Since for the given equation this condition holds, so equation 1 is exact. Now the solution of the question is given by integral of m dx, where y is constant, plus integral terms of n free of x into dy is equal to c. Putting the value, this is value of m in terms of n free of x. In this value of n here, for n we have two terms, and both the terms have x, so we will not take any term between the two. Here we have two terms, both the terms have x, so we cannot take any term from these two terms. So here we can take 0. Integral of m, so this is the value of m. Terms of n free of x. Here we have no term which is free of x, so here the result is 0, and is equal to c. Now integral of y with respect to x is equal to xy, plus integral of 2xy square with respect to x is equal to 2x square over 2 into y square. Simplifying, this is the general solution. This is the general solution applying the given condition. Y is 1 when x is 1, putting these two values here, so value of c is equal to 2. Now putting value of c in the general solution, so the particular solution is xy plus x square y square is equal to 2. This is the particular solution, this is the general solution. Another question, determine if the equation is exact. If so, solve it. This is the differential equation. If it is exact, then we have to solve. So in this equation, the first bracket is m, the second bracket is n. Derivative of m, partial derivative of m with respect to y is equal to this one. Partial derivative of n with respect to x is equal to this one. Here, del m over del y. So derivative of y with respect to y is 1, cos x is constant. Similarly, derivative, partial derivative of e power y is e power y, 2x is constant. Similarly, del n over del x. So derivative of sine is cos, and derivative of x square is equal to 2x, e power y is constant. Derivative of minus 1, partial derivative of minus 1 with respect to x is 0. Here we see that value of del m over del y equal to del n over del x. Thus the given differential equation is exact. The solution is integral of m dx, where y will be constant, plus integral term of n free of x dy is equal to c. So value of m, this m will be here, and we have to take those terms from n which is free of x. So this is n, and we have to take that term which do not have x. Here we have x, so we will ignore it. Here we have x, we will ignore it. Here we have no x, so we will take it. So this minus 1 will be used here. Now integral of this term is equal to, that is integral of cos with respect to x is sin x. Here integral of x with respect to x is x square over 2. Integral of minus 1 dy is equal to minus y is equal to c. Simplifying, this is the general solution. This is another question. This is not, this is cross, this is something misprint. This is the question. Here the differential equation, this is the differential equation, and we have to solve this differential equation. So simplifying the differential equation, we can write x dx, this is x dx plus y dy equal to this expression divided by x square plus y square. Now simplifying, so we can write this. Here we have first term divided by the divisor minus second term divided by the divisor. Now rearranging, this is the here we have all x, here we have all y. Now we have to transpose this term to the left side, so this is the transpose. This minus will become positive, this positive will become negative. Dy equal to 0. In this differential equation we have m, this is value of m, this is value of n. Now differentiate m with respect to y, so partial derivative of x with respect to y is 0, and using quotient rule for this term, so a square, now square of denominator partial derivative of numerator minus numerator partial derivative of denominator with respect to y. This is not x, this is y. So x square plus y square, this is x square plus y square, del y over del y is 1, and partial derivative of x square plus y square with respect to y is 2y. So 2y and 2y is equal to minus 2y square. Simplifying, so this is the value of del m over del y. Now we have to differentiate n with respect to x, so this term will be 0, and we have to use quotient rule with respect by using partial derivative with respect to x. So del m over del x, derivative of y with respect to x is 0, and use quotient rule for this term, minus a square, square of denominator derivative of x with respect to x, which is 1, minus numerator derivative of denominator with respect to x, x square plus y square, derivative of x square plus y square with respect to x is 2x. Simplifying, this is the simplification, taking this negative sign inside, so we can write x square minus y square divided by this one. We see that value of del m over del y and del n over del x, both the values are equal, hence the given differential equation is exact. Now the general solution is integral of m, where y will be constant, plus integral of terms of n not containing x, dy is equal to c, putting the value, this is value of m, and take those terms of n which do not have x. So let's see, this is n, we have to take that term which do not have x, so we will ignore second term and we will take first term because it is free of x. So free of x, the terms of n free of x is y. Now we have to differentiate. Integral of x with respect to x is x square root 2. Similarly a square y, here integral of 1 over y square plus x square dx, integral of y as y square over 2 is equal to c. Now we can write y square plus x square is 1 plus x over y whole square. This y square is here. Now let us simplify. Let us take x over y is equal to t. Differential of x over y is equal to differential of t, and this will give 1 over y dx is equal to dt, that is dx is equal to y dt. Putting the value, equation 2 will become x square divided by 2 plus a square y divided by y square. Integral of dx is equal to y dt. Integral of 1 plus y over x whole square will become 1 plus t square, and this plus y square over t is equal to c. Here the this y and this y will be y square, and it will be cancelled with y square. So look, this y both will be cancelled with this 1, and we will get x square divided by 2 plus a square integral 1 over 1 plus t square dt is equal to y plus y square over 2 is equal to c. Here integral of 1 over 1 plus t square dt is equal to tan inverse t, and simplifying and putting value of t. So this t is x over y, and here we have dou c. If we multiply both sides by 2, here we have dou c, and that dou c have been replaced by c1. So this is the general solution. Now we have to solve few questions from this exercise. Test for exactness. If exact, solve. This is the differential equation. Here m, this part of the differential equation is m, and partial derivative of m with respect to x is equal to this one, del m over del y. So derivative of y square is 2y, and we will get 4xy. Derivative of 3x square with respect to y is 0. So this is the partial derivative of m with respect to y is this one. Similarly, this is n. This one is value of n. Del n over del x will be equal to 4xy, since value of del m over del y equal to del n over del x. Thus the equation number 1 is exact. This is equation 1, and it is exact because the necessary condition for exactness is satisfied. The solution is integral m plus integral of terms of n free of x dy is equal to c. Here this is not x, this is y. This is y. This x is not x, but it is y. Dy is equal to c. Now integration of 2x y square with respect to x is 2x square y square over 2 plus integration of 3x square is 3x cube over 3 is equal to c. This 0 is because we have no term in n which is free of x. We have to take that term from n which do not have x. Since it has only one term having x, so we will ignore every term of n. So here is 0. Now this is the general solution. Another question. This is the differential equation. Taking this part is m and this part is n. If we differentiate this with respect to y, so del m over del y is equal to, this term will be 0. Hy, derivative of hy with respect to y is h. Derivative of g with respect to y is 0. Now this part is n, differentiating with respect to x, so del n over del x is equal to h. Other terms will be 0. Since value of this is equal to value of this, both the values equal to h, hence equation 1 is exact. The solution is integral m plus integral of terms of n free of x dy equal to 0. Putting value of m. Value of m is this one, and here we have to ignore hx because this term has x. We have to take by because this term is free of x. We have to take f because it is free of x. So we have to take last two terms. These last two terms are here. Now integral of ax with respect to x is ax square over 2 plus integral of hy with respect to x is hxy plus integral of g with respect to x is equal to gx. Similarly, integral of by with respect to y is by square root 2. F will become fy is equal to c. So this is the general solution. Another question, this is the differential equation. First part is m, second part is n. Differentiation of this equation with respect to y. If we have to partially differentiate m with respect to y, we have to treat x as constant. So partial derivative of m with respect to y is 18 xy square. This is n. Partial derivative of n with respect to x, we have to treat y as constant. So this term will be 0, and here we will get 2 9s are 18x y square. Since value of m del m over del y equal to del n over del x, hence equation 1 is exact. Now we have to write the general solution. This is the formula. The general solution is integral of m with respect to x, where we will take y as constant, plus integral of terms in n not containing x into d is equal to c, putting the value, this is value of m, and this term, this is the term in the function n free of x. So we can write, looking to n, here we have two terms. The first term is free of x, so we will integrate. The second term have x, so we will ignore it. So this is the term free of x. Now integrating this with respect to x, so we will get jx square y cube divided by 2 plus 4 y4 divided by 4 is equal to c. Simplifying, this is the general solution. So in this here we have discussed a few example and few questions about exact differential equation. Whenever we have to check a differential equation to be exact or non-exact, we have to check whether del m over del y equal to del m over del x. In case for a differential equation, if it holds, then we have to use this formula for the general solution. Thank you.